In this example, we are going to apply our new understanding of the basic and different mechanical properties that are of interest in our design of structures. All right, so we're given a stress strain curve for a particular material. We've got the proportional limit stress we're going to be asked to go find, the yield stress, the ultimate strength, the rupture stress, and the modulus of elasticity. So note, we've already been given stress versus strain. Stress is in KSI, so not the force on the member, but rather the stress on the material, stress in KSI, and we have strain, which is inch per inch, but we need to take this number that's here and multiply it by the 10 to the minus third. Strain values are usually very small, not typically large numbers, right? And so remember, this is inches of deformation over original length, hence why they're on the small side. Sometimes this is micro strain, that would be 10 to the minus 6. Now, one of the things you also have to figure out when you look at these kinds of numbers is, have they already multiplied by times 10 to the minus third when I look at this, which means I have to divide by, or do I need to multiply 20 times that? And I look at the scale and I know these are too big already. I need to multiply them by that small 10 to the minus third in order to get a reasonable value of stress. But that can sometimes be confusing about how to interpret this. All right, let's get into some details here. We're first asked to find the proportional limit stress. That's when we no longer have linear elastic behavior. Now, this is a little bit something you have to do by eye. And your answer might be slightly different than someone else's, and you might both be, well, reasonably accurate. Now, see, please understand here that in real materials and real data, it never looks this smooth. It's a lot more jagged. And so you sometimes have to take the same material, test it many times, and look at the aggregate of all that, maybe finding averages or other kind of value to finally settle on, as a community, what we're going to take for some of these various values. They're never this pristine and clean as we see here. Our purposes it is. So note that it looks to me like our limit of linear elastic behavior is right about at that 40 value. So our proportional limit stress, I think, reading by eye, is right about 40 KSI. That's the end of linear behavior. And you might have come up with 41, 42. I could see someone arguing back and forth roughly there. Sometimes what I do is, and oftentimes really I do this, I put my straight edge up there, and that's where I can begin to see that line beginning to curve away. Maybe if you plot the line with a slightly thinner width, it's a little easier to see when it bends over. Right? But notice this is a very smooth transition. So because of that, what the yield stress is, where we begin to have permanent deformations, is not so clear. And in instances like that, we use what's called the 0.2% offset method. Now 0.2% is the same thing as 0.002. And that is the same thing as 2 times 10 to the minus third. So what we want to do is go right here to 0.002 or 0.2% on the strain curve, and we're going to draw a line that is at the same slope as the linear elastic region. Right, now the way you really are supposed to do this is you get two straight edges out, and so what I'll do is I'll set a reference here with this ruler and I'll slide this down. This is how I assure that we actually have a parallel line, at least from a graphical kind of perspective. Right? There's some other ways we could mathematically do this, but this would be a typical graphical approach. Yeah, if I'm off a little bit, then where I'm going to intersect up here at the top is going to change a little bit, and maybe it seems like it might change a lot. It's slightly below 50, and it looks to me like by scale that's going to lead to a yield stress at 0.2%. That's going to be about 48 KSI. You might do it and come up with 49. Doesn't look like it's quite 50 to me, because this line never really quite gets up to that dashed line that represents the 50 axis. Small little variations here are not going to have a huge influence It will on the strain value, but not on the stress value that goes with it. So we're going to all be right around maybe 47, 48, 49 KSI. The ultimate strength here is that peak on the entire system, and that's going to be very close here to 49 KSI. It's going to be slightly larger than what we had before for the 48. There's going to be some sort of change, and definitely higher than the proportional limit that we've got. The rupture stress is the stress that is associated all the way out here at the end, or where we have fracture. And so there we just got to go out and try to do a good job of interpreting, scaling what we've got. You could get your scale out and try to even do that better. I'm going to do it by eye. It looks like it's just slightly less than halfway, so I'm going to call that then sigma r is equal to about 34 KSI. You might say 35, and you wouldn't be wrong. I don't know if either one of us is right, but neither one of us would be wrong. We'd be pretty close to each other, especially, doing this by eye in this kind of format. And then we get the modulus of elasticity. That's our E. That's the slope of the linear elastic region for at least that initial one here, Young's modulus. And there what I'm going to do is not try to go find it over a small region. Since this looks like it's already been adjusted to pass through 0 stress, 0 strain, and we've identified, we think the end of it is up here at 40 KSI, and that happens to be real close to that strain. Well, okay, so let's just do delta sigma over delta epsilon. That would be 40 KSI minus 0 KSI over then 0.004 inch per inch minus 0. And we'll then get, of course that's just 0.004, and that will tell us that our elastic modulus is going to be 40,000 KSI per inch per inch. A lot of people won't put that inch per inch at the end. It really is there to make the units in our equation for Hooke's law work out properly, because remember, Hooke's law is sigma equals E epsilon, and so for units to work out, we want stress here, we have inch per inch here. That's why the units on E properly are KSI per inch to make that work out. 40,000 KSI for a stiffness is fairly high, much higher than, say, steel, which is 29,000 KSI, but typical of metals. It's all in that sort of ballpark of metals.